So today we're going to be looking at a geometric series. Now, a geometric series is the first example of a type of power function, or another way that we could describe it is an exponential graph. And so without further ado, let's jump into the generic formula of a geometric series. Now you notice this looks a lot like the exponential form, and if you're familiar with exponential form, you'll remember that y equals a times b to the power of x. We're seeing something very similar here, a starting value, a growth rate, and a power. Starting value, growth rate, and a power. So let's go ahead and describe that. For our a to the nth, this is the term in the pattern that we seek. So the number or the term in the pattern we seek, whether that be the 10th, the 100th, or the 1000th. Doesn't matter which position we're going after, this is what holds the place of that. Likewise, a to the 1 is going to be our starting value. So this is our, let's not do that in red. Let's do this in, let's see. Yeah, why not orange? So a to the 1 is the first term. So the first term in our pattern. Perfect. The r, similar to how we did the arithmetic series, r is going to be our rate of change, but it's not just any rate of change. Because this is an exponential graph, this is our ratio, or our rate of curvature. It's not a line, so we're not necessarily going to call that a distinct rate of change. We're going to call this our rate of curvature. And then lastly, our n is going to be this position, or the position, or spot in the pattern we want. So if we want the 10th, n is going to be 10. If we want the 100th spot, n is going to be 100. And there we go. So we have these four variables. What we're going to do down here is we're going to create a formula using this and predict a future term. So write the formula out, and we're going to predict the 5th and the 15th. Now, one of the things you will notice is that with geometric patterns, they tend to get out of hand very quickly, very fast. So we're limiting ourselves to the 5th and the 15th. Now, both of these, there we go. Zoom is a little sketchy right now. Both of these, we can actually kind of go out to the 5th without using the formula, but again, this is good practice for when we want to go a little further. So for this one, this is 1, 2, and 3. It looks like I'm doubling, which means I could just double 2 more times and get that using the brute force method. That would be 8, 16. So no work necessary. I'm at position 16. But again, we're practicing this so that later on, we can use the same method for, let's say, the 100th, the 2000th, anything like that. So let's take a look at how we're figuring this out. I want to find the rate of change between these three terms. So the way that I can figure that out is I'm going to take any term and divide it by the number before it. So 2 divided by 1 and 4 divided by 2. 2 divided by 1 is 2, 4 divided by 2 is 2, which means our rate, or our rate of curvature, is going to be a positive 2. Perfect. Well, that's pretty much all we need to figure out the formula. We know a to the nth is equal to a to the first times r to the n minus 1 power. Okay. So a to the nth is going to be equal to the first number in our pattern, which in this case is going to be the number 1. And we are going to be multiplying it times the rate of 2, however many times we need to get to the position that we want. Okay. And unlike with the arithmetic series, I can attempt to simplify this, but really, that's just it. I take the first number, I multiply by 2, however many times I need. The reason why we're subtracting 1, again, is because for the first term, I'm not actually multiplying by 2 just yet. So 1 minus 1 is going to lead to 0, and that whole term is going to cancel out. And I'll be left with 1 the first term. But let's use this formula right here to predict the 5th and the 15th, which tells us two things. N for the first one is going to be 5, and N for the second one is going to be 15. So let's go ahead and copy down our formula and plug in a 5 and a 15. So the 5th term, which we know via the brute force method, by doubling this 2 more times, is going to be 8 16. We should get a 16 for our answer right here. Oh. So let's go ahead and say, okay, my first number is 1. I'm doubling it 5 minus 1 times, which means I'm taking my first number and doubling it 4 additional times to get to the 5th spot, which is 1 times 2 to the 4th power. 1, 2 to the 4th power. At this point, I'm going to break out the handy-dandy calculator. So let's see, 2 raised to the power of, where are we going on here? We should have a y to the x button somewhere. There we go. Raised to the power of 4, we get 16. Perfect. So the 5th number in our series is 16, just like we predicted. Awesome. For the 15th term, we're going to do the exact same thing. A subscript 15, which means the 15th number is going to be 1 times 2, 15 minus 1 times. Taking that first number and I'm doubling it 14 additional times to get to the 15th spot. So I'm raising it 14. So 2 to the power of 14. 16,384. Which is 16,384. Perfect. There we go. Okay, so now what I want you to try is I want you to go ahead and give number 3 a shot. Go ahead, try it out. Pause the video, unpause it when you're done, and see how well you did. Okay, assuming that you've given it a shot, one of your first things you might have run into, and we'll do a secondary pause here in a moment, is getting through this. We notice that with this, when I do my division, -6 divided by 2 is -3. 18 divided by -6 is also -3, which begets a rate of -3. With a negative value, we notice that our numbers go up and down, up and down, up and down. So it's not necessarily going to give us the nice, neat responses where we notice the numbers got bigger, like we did in the ones above. So if we were to write out our formula, a to the n equals a1 times r n minus 1, a to the n equals my first number, which in this case is a 2. I'm multiplying this times -3, some number minus 1 times. Perfect. And so as we slide to the side, actually let's give some room for the calculator eventually. I want to figure out the 5th term and the 15th. So if you struggle to get through this piece, go ahead and try it out now. If not, we're going to jump into this. So my 5th term is going to be equal to 2, because that is the first number in my series, right here, times our -3, 5 minus 1 times. So I'm taking 2 and I'm multiplying by -3 4 additional times to get to the 5th spot. So 3 to the power of 4. Let's see what that gives us. 3 to the power of 4, it's going to give us 81. If we multiply that times 2, we get 162. Perfect. So if we do this with a to the 15th is equal to 2 times negative 3, 15 minus 1 times, which means it's 2 times negative 3, 14 additional times to get to that 15th spot. So let's see what this number is. Ooh. Almost missed that. Luckily, this didn't change up. By the fact that we're raising a negative 4 times, that's an even number. That'll still end up being a positive. However, for this one, again, yeah, we have an even number, so not a big deal. But just to show, if we take negative 3 and raise that to the 4th power, positive. If I take a negative 3 and raise that to the 14th power, we'll get a big number here. 4,782,969 times 2. 9,565,938 is our 15th spot. Perfect. Okay. So we see all really a geometric series is you take the number, you figure out the rate, and you do that one less time than the position. So that way you can get into the position as opposed to overtaking it. The last question that we're looking at is what would a graph of a geometric series look like? We've talked about how the fact that this is also called an exponential curve. So we have 3 options. We have an exponential curve up or an exponential curve down. Perfect. So these are both starting positive geometric growth / decay. So if we start at a positive number, geometric growth, starting at a positive number, geometric decay. We have starting negative, with geometric growth. Actually, the first one is decay and growth. Perfect. And then the last one is going to be a divergent. So we have one with a whoosh, 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 whoosh. And then we have another one where it starts like that and then it goes up. So this is, doesn't really matter which one we have. We have negative growth rates. One, the negative is less than 1, so less than 1, and one that is greater. Perfect. There we go. So our geometric series do look a little different than our lines like before. There we go.